Hello everyone, this is Mrs. Aparna More from Modern College of Engineering, Pune. Today we'd like to discuss on digital to analog converters. It is a form of data converters. Now what is data converters? Data converters is a converter which will convert one form of data to the other. That is, it can convert a digital signal to an analog or an analog to digital, or it can convert a voltage signal to a current signal or a current signal to a voltage signal. So we have data converter classification here. It is classified into two types, that is D2A converters or A to D converters. D2A converters, that is digital to analog converter, is classified into two types, that is weighted resistor DAC or R2R ladder DAC. Analog to digital converter is classified into flash type ADC, counter type ADC, single and dual slope ADC, and successive approximation ADC. Now digital to analog converter is here as we see in the diagram that it has four digital inputs, that is D1, D2, D3, D4. D1 being the MSB and D4 is the LSB. Here we have the reference voltage. It can either be a positive reference voltage or a negative reference voltage which is given to the input of the DAC. The output of the DAC is analog output voltage signal. So this is another form, that is digital input V reference and the output is in analog signal. Here we have to observe that analog signal is equal to V reference into D1 2 raised to minus 1 plus D2 2 raised to minus 2 plus so on up to Dn 2 raised to minus n. We will see how these terms come in the next slides. As we had seen that the types of DACs are binary weighted resistor DAC and R2R ladder DAC. Now this is an n-bit binary weighted resistor DAC. In this we can observe that there are n number of digital inputs, that is D1, D2, D3, D4 so on up to Dn, where D1 is the MSB and Dn is the LSB. To the digital inputs we have the switches which are connected. So these are the toggle switches which are either a 0 or a 1. The switches are connected to the reference voltage. Please observe that the reference voltage is negative here and the other switch like switch 1, switch 0. So the other term is connected to ground. This other part of the switch is connected to the resistor. Now these resistors are the weighted resistor. If you observe carefully, the resistor, each resistor has a weight. That is, this resistor has 2 raised to 1, this resistor has 2 raised to 2, this resistor has 2 raised to 3, so on up to 2 raised to nr. The other point of the resistor is connected to the inverting terminal of the inverting summing amplifier. This is an inverting amplifier if you observe. Then here we have RF. RF is the reference voltage. The output is nothing but the analog output signal. So this is the circuit diagram for an n-bit weighted resistor DAC. Now here the current IO is flowing from the output signal to the input. So we have IO. If you see here that this point A and this point, so positive point, this one is connected to the ground. So this point is connected to the ground. So obviously due to virtual ground concept, this point is also connected to ground. That means here also the voltage is 0. Now here we have IO, which is divided into the currents I1, I2, I3 and IN. So IO is divided into I1, I2, I3, so on up to IN. The reason being that it cannot be going to the input of the amplifier, because as we consider this as an ideal op-amp, the ideal op-amp has high input resistance, so the current is going to be 0. So we have the current going here is 0. So obviously IO flowing here is divided into I1, I2, I3, so on up to IN. So the description is written over here. Then we have n-bit resistor DAC, the value how we find out VO. As we have seen that IO is equal to I1 plus I2 plus I3 plus so on up to IN. Now to write the value of I1, I2 in terms of voltage and resistor, we have I1 is written as 0 minus of minus VR upon 2 raised to 1 R. As we had discussed that this point is 0. So I1 is equal to 0 minus of minus VR. This is minus VR, so we will write 0 minus of minus VR upon 2 raised to 1 R. Likewise, I2 will be written as 0 minus of minus VR upon 2 raised to 2 R. I3 is written as 0 minus of minus VR upon 2 raised to 3 R. So we will see here, all these terms are written here. We take out VR upon R common, and it will be d1 upon 2 raised to 1 plus d2 upon 2 raised to 2 plus so on up to dn upon 2 raised to n. Now the output voltage is written as VO is equal to IO into RF. Substitute the value of IO as VR upon R into the bracket terms. So here we have VO is equal to VR into RF upon R into bracket d1 upon 2 raised to 1 plus d2 upon 2 raised to 2 plus so on up to dn upon 2 raised to n. If we consider RF is equal to R, that means both the resistors having same values, then VO, that is the output voltage, is equal to the reference voltage into D1 2 raised to minus 1 plus D2 2 raised to minus 2 plus so on up to Dn 2 raised to minus n. So we have found out the equation. Now we'll consider the 3-bit binary weighted resistor DAC. Generally, the question asked is explain binary weighted resistor DAC. So we can go for 3-bit binary resistor DAC. In the 3-bit binary weighted resistor DAC, we have three inputs, that is D1, D2, D3, D1 being the most significant bit, MSB, and D3 is the LSB. So D1, D2, D3 are connected to the switches. Here we can see these are the switch. One point of the switch is connected to minus VR and the other point is connected to ground. Now here the switches are connected to the weighted resistors. The weighted resistors are 2 raised to 1 R, 2 raised to 2 R, 2 raised to 3 R. The other point of the resistor is given to the input of the amplifier. Here we have RF, which is connected between the input and the output, known as the feedback resistor. Here we have used inverting summing amplifier. So we can write the equation as, here IO is equal to I1 plus I2 plus I3, as I going into the input of the op-amp is 0. So for this, we have IO is equal to I1 plus I2 plus I3, as we had seen. I1 is written as, we had described it in the n-bit binary weighted resistor DAC, that I1 will be 0 minus of minus VR upon 2 raised to 1 R. I2 will be 0 minus of minus VR upon 2 raised to 2 R. So we will substitute directly the value, that is VR upon R d1 upon 2 raised to 1 plus d2 upon 2 raised to 2 plus d3 upon 2 raised to 3. This is the value of IO. The output voltage VO is written as IO into RF. Substitute the value of IO, which is written here over here. So it will be VR into RF upon R into the bracket terms, that is d1 upon 2 raised to 1 plus d2 upon 2 raised to 2 plus d3 upon 2 raised to 3. If we consider RF is equal to R, then the value of VO will be VR into the bracketed terms. Suppose if we consider D1 as 0, D2 as 1 and D3 as 0, that means here D1 as 1, which is connected to the VR, D2 as 0, which is connected to the ground, and D3 as, here we have written as 0, so D3 is also connected to the ground. So in that case, what will be the value? We have to substitute the value of D1, D2 and D3 into this equation. So VO will be VR into bracket 1 upon 2 raised to 2. Likewise, we can take any input. This is a reflection spot wherein we will just discuss about the values that we have given and find out the answer for VO. So the D1 value is 1, D2 is 1 and D3 is 0. So for that, we have to find out the analog output voltage considering RF is equal to R and minus VR is equal to minus 5 volt. That means the reference voltage given is minus 5 volt. So I'll pause for a while, and till then we can find the answer and then we can check it. So if we put the value of D1, D2 and D3 into this equation, so here we have VO, which is equal to, here it is 5 volt, 5 into bracket D1 upon 2 raised to 1 plus D2 upon 2 raised to 2 plus D3 upon 2 raised to 3. And the answer for that will be VO is equal to 3.75. So I hope you've got this answer. Now this is the truth table for D1, D2, D3, that is 0, 0, 0 to 1, 1, 1. So for all the values, the analog output voltage is written here. If we consider the graph for digital input versus the analog output, over here we see that the digital input is marked on the x-axis and the analog output is marked on the y-axis. So we will be writing 0, 0, 0, 0, 0, 1, 0, 1, 0, so on the x-axis, and the output which we have obtained on the y-axis. If we plot the graph, you see that it is in a staircase form. So this is the graph for the 3-bit binary weighted DAC. This is the explanation for it that we have discussed. Now, considering binary weighted DAC, there are some disadvantages to it. That is, if we increase the number of resistors, then the value, that is the binary weight to it, will also increase, thus making it a very complex system. Also, the accuracy of the resistances is to be considered. So if we take more number of resistors, the accuracy is slightly not to be stable. So the accuracy and stability of the DAC depends on the accuracy of the resistors, which will be difficult if we take more number of resistors for more number of digital inputs. Thus, considering R is very large, the op-amp bias current gives a drop, which is the offset output voltage. So here, considering these disadvantages, we have another type of DAC, that is R2R ladder DAC, which will be explained in the next video. The references that I used is Ramakant Gaikwad, op-amp and linear integrated circuits. Hope you find this video good. Thank you.